remember the Fourier sine series or cosine series? What did that look like? So you were trying to express a function as sum of sine functions, right? With n pi over Lx. Something like that, right? And in the special case when the length was 1, L is 1, you had this. N goes from 1 to infinity. And there are two things about it. First of all, the fact that any function that's defined from 0 to L, or 0 to 1 for this case, any function defined from 0 to 1 was able to be represented as sum of the sine functions, right? That's one thing. And another thing was these bn's, we were able to calculate them by using orthogonality, right? So what was the formula? It was 2 over L, 0 to L, f of x, sine n pi over Lx. In the case when L is 1, this is simply just that, right? dx. So that's how you were able to get it. And that made this formula useful. I mean, what's the point of having this if you don't know how to find the coefficients, right? And we needed this because we later found out that when you solve the heat equation or wave equation or some PDE using separation of variables, you get all these building blocks for the solutions, and you only know how to solve the equation when your initial condition can be put into this form, right? As some of these building blocks, right? That was the idea, right? So something similar is going to happen to us when we try to solve the wave equation on the disk, okay? Last time we stopped just before seeing that the equation we get is the Bessel's equation, right? So we know that the building blocks involve Bessel functions when you try to solve wave equations using cylindrical coordinates or polar coordinate system. So we need to have something similar like this, except instead of sines or cosines, which Fourier originally used, for us we need to use the Bessel functions. And that's why such a series is called Fourier-Bessel series. And Fourier comes because the idea is the same as the Fourier series, but Bessel is used because you're trying to express any function as sum of n equals to, k equals to 1, infinity of a, k, j, n, j, n, k, x. That's called the Fourier-Bessel series. Now, see, what's sine of n pi?
0.
It's the nth zero of sine, right? So if I replace n by k so that it looks more like that, you can really think of this as the kth positive zero of sine, right? That's exactly what I have here. That's the kth positive zero of the Bessel function. So there's the correspondence, right? And this will allow a function defined from 0 to 1 to be expressed like that. And of course, if you want something that works from 0 to L, then you have to divide this by L, and the formula will change. Okay, so, right, but for simplicity, let's just take L to be 1 and then proceed with the calculation. And you probably, it's not too hard to figure out what to do if L is not 1. Okay. All right. So we have that series is called the Fourier Bessel series. But again, if you don't know how to get the coefficients AK, what's the point, right? You have to know how to find it. But in order to find AK, you need to know orthogonality relations. Okay? So here are the orthogonality relations for the Bessel functions. Where did I have it? So, orthogonality relations. These are integral from 0 to 1 of x times j and j and k x times j and m x dx is going to equal to 0 if k and m are different. So I explained that for the sine function, sine times sine n theta times sine m theta, if you integrate from negative pi to pi, this gives you 0 when n and m are different, right? And I explained that this is like a dot product between two functions. There's this theory of L2 functions and stuff like that, right? So it's like dot product between two functions. And if the dot product is 0, that means the two vectors are orthogonal, right? So that's why it's called orthogonality relations. That if k and m are different, then their dot product would be 0. Now, you might see something strange about this one compared to this one. What is it? It's this x, right? So there's this extra x there, and what actually happens is that as long as you put any positive function here, that can still be considered as an inner product. So it's like the dot product, but with some kind of a weight. So this thing here is called a weight function. And in our case, the reason that x is there is because these decrease like 1 over square root of x, right? We talked about that. The amplitude decreases like 1 over square root of x. And by multiplying by x, it gets rid of that decrease and somehow makes it look like a regular orthogonal function. So that's what happens, right? Okay. So that's what I want to say. And hopefully at the end of the semester, maybe in the last class, I can show you that these functions happen to be solutions of some Sturm-Liouville problem. And for any Sturm-Liouville problem, there's always this weight function times those two functions, and if they are different, then they're orthogonal. You can show that for any Sturm-Liouville. So I'm going to prove it for this specific one, but the proof that I'm showing you is pretty much how you do it for any Sturm-Liouville. Okay. What's harder would be, what if k is equal to m? Well, we know that it's not going to be 0, because if k and m are the same, then you have something squared, right? If these are the same thing, it's something squared. A square function is always positive, or 0. And if you integrate over some domain, it can never be below the x-axis, so the area under the curve will always be some positive value. That we know, right? So we know it's some positive value, but it takes quite an effort to figure out that this actual value is 1/2 jm plus 1, k plus 1. of j and k, then this thing squared. So this is what happens. And that will allow us to figure out what these AKs will be. Right? So let's figure that out. Okay, so yes?
That means GNK x, when x equals to any integer, gn equals to 0, right? Or
X is any integer.
the gnkx equals to 0.
J and kx. No. If x is 1,
Only 1.
then yeah, 1.
Okay.
Yeah, if you plug in 1, then this. Gives you
It's different with
yeah,
the
no,
sign.
it's
Yeah, I just want to.
it's almost equally spaced. So the thing is, I said Bessel function is like the sinusoidal function that has decaying amplitude. So you might have the impression, oh, that means that the zeros will be like equal multiples of each other. It's not really, but eventually, when x becomes very large, then it will behave more equally spaced. But it's not exactly equal. Yeah. All right. So let's try to prove this. And to prove this, we need to use something that we had before. So u double prime, no, let's see, y double prime plus, actually, x, no, r squared. Let me write it down as the one that we got from the wave equation. So r squared, capital R double prime plus small r, capital R prime, plus we had something like, let's just put, I think we had mu there, but let's just put a squared r squared minus n squared capital R equals 0. So this is something that we obtained while solving the wave equation with separation of variables. You can find it in your notes a few pages before. Okay, so we had that before. And then what we did was, if you do a change of variables with x equals to a times r, in the notes I had mu times r, but Greek letters make things look very hard, so I'm just using a. It's easier, right? Okay. So if you do that, then what happens is that this equation turns into like x squared r double prime plus xr prime plus, basically the a gets absorbed. And we know that this is what's called the Bessel's equation, whose solution is like C1 jnx plus C2 ynx. This is a Bessel function of the second kind, but this is non-physical, so we ignore that one and we just take that as a solution, right? And then you go back to the original one, and that the solution is jun ar. So that's what we had before, okay? So I'm going to be using this again. And the way we are going to use it is, first of all, this looks overly complicated. So let's call this one as A, and let's call this as B. Okay? And let's talk about, let's rewrite u of x as jn of a times x. Is that okay? So I'm just calling this one as u, and this one as, I'm going to call it as v of x. So one thing you get out of this is that u1 will be 0, and V1 will also be 0, right? Just because if you plug in 1, it's Jn evaluated at one of the zeros, so that's what you know. Right? So we have those, and because this one is like this one, right? This is going to satisfy this equation. Instead of r, you just have x, right? So u of x is going to satisfy the following equation. It'll be x squared u double prime plus x u prime plus a squared u x squared minus n squared u equals to 0. Is that okay? Yes.
I don't understand why you can write this as x squared. So if x equal to ar, so r.
No. Sorry. So now x is r. Okay.
Oh.
Sorry, it's a bit confusing. Okay. You know what? Just forget this what I wrote here. Just remember that our result was that the solution of this was r equals to C1 Jn A times r. Is that okay? Yeah. So, and along the way there was some change of variables that we had to do. We worked that out in like actually in the last lecture we worked that out. Okay. But let's say if we know that, then all I want to do is I want to replace the capital R by U, and this A and A same, right? And small r by x. So that's the equation that it solves. Is that okay?
I'm going to change the just replace r by x.
Yeah, just take this result, replace small r by x, capital R by u.
Okay.
And then that's what we have. Okay? Alright, so, and the same thing happens for v. So let's write down the formulas for the equations for u. Now what I'm going to do is I'm going to divide everything by x squared and rewrite it as u double prime plus 1 over x u prime plus a squared minus n squared over x squared u equals to 0. And I'm going to write down the same thing. V double prime plus 1 over x v prime plus b squared minus n squared over x squared v equal to 0. Now notice that because vx is b times x, it's no longer a, but this is b. Right? Is that okay? And we are trying to do the case when a and b are different. I want to show this one, 0. Okay. All right. So having this, now what we do is we multiply this one by v, and we multiply this one by u, and subtract. Subtract that. And that's going to give us, what is that? U double prime v minus v double prime u. Okay. And plus 1 over x times u prime v minus v prime u. Okay. And then uv with n squared over x squared and vu with n squared over x squared. If you subtract, they're going to cancel away, right? So those are going to go away, and these will survive. So what you get is plus a squared minus b squared, and you're going to have uv equal to 0. now you do something funny. You take u prime of v minus v prime of u. You take this one, and let's see what happens if you differentiate this using product proof. So what is u prime v prime? That's u double prime v plus u prime v prime. And then minus v double prime u plus v prime u prime. That's equal to
u double prime v minus v double prime u.
hey, that's exactly the same as that one, right? You get that? So that's nice. So with this, you can rewrite this one as u prime v minus v prime u prime plus 1 over x u prime v minus v prime u. And let's move this to the other side and write it as b squared minus a squared uv. So if you move it to the other side, then you get negative. So instead of a squared minus b squared, you get b squared minus a squared. Okay. So aside from the fact that uv appears here again, if you just look at these, the left side here, that looks like a first order differential equation, right? Is that right? First order differential equation. And you can take the multiplier and multiply it to the left side to turn it into product rule. Okay, let's not go there. Well, rather than doing it that way, just observe that if you multiply by x, then this is a product rule, right? Because you can, this is 1, but 1 is x prime, right? So you have f of x times g prime of x plus f prime of x times g of x. So I can rewrite this entire thing as d dx of, okay, let me see if you understood. Of what? X times
u prime v minus v prime u.
Okay. Is equal to b squared minus a squared x uv. Now this is perfect because remember this was our u, right? This is our v, and there's a x. So you have x uv there on the right side. What should we do now? We integrate both sides from 0 to 1. Which means that x times u prime v minus v prime u, 1 and 0, okay, equals to, you pull the b squared minus a squared out, integral from 0 to 1, x times uv dx. Okay. Now what's v of 1? The proof is so long, I'm trying to test if you remember.
0.
V of 1 is 0. What's u of 1?
0.
Yeah. Because v of 1 is what? You plug in 1 here, so j and m of 1. But j and m by definition is the 0 of jn, right? So it's going to be 0. If you plug in 1 into v, you get 0. If you plug in 1 into u, for the same reason, it's 0. Yes?
Should the right side of the integral, from 0 to 1, b squared minus a squared x uv, be b squared minus a squared uv, because you are taking the derivative of the left side. It's only the left side. Right side didn't really do
Yeah,
anything.
we didn't do anything. I have the equality without the integral sign, right? And I'm integrating, and then the left side, the integral cancels the derivative. But on the right side, it's just this integral, where this is a constant. A and B's are constants, right? A is really J and K, and this is J and M, which is just a constant, so I bring it outside. Okay, so when you plug in 1, these are zeros. Then when you plug in 0, these might not be zeros, however, this will be 0, right? Yeah. If you plug in 0 in here, it's 0. So that's it. We know that this side is equal to 0. And since we are assuming that B and A are different, right? So you cancel that out, and we get this result.
Wait, I still have a question.
Yes.
If you take derivative first and then integral the left side, you should do the same operation to the right side, right? So
No, there is, I'm not differentiating, I'm saying that this itself is equal to the derivative of this thing.
Oh.
If you apply the product rule to this, if you do the product rule of this, what happens? Yeah, maybe I forgot a parenthesis, that's why. If you apply the product rule, it's f g prime, which is this one, plus f prime g, which is this one. Right?
Oh, I see.
Yeah. So I'm just rewriting that one, and I didn't do any derivatives here. Okay, good. It's good to have those questions. Yeah. All right. So that proves this 0. Okay. Now the harder part, which is if K and M are the same, then what value do I get? Right, so in that case, I'm going to start with the equation for u, which is x squared of u double prime plus xu prime plus a squared x squared minus n squared u equals to 0. Okay. So u double prime. Okay, so what I'm going to do is I'm going to multiply this by 2a squared u prime. So multiply everything by 2a squared u prime. And you know, a lot of the proofs and analysis is really just integration by parts. But what is integration by parts? It's like undoing the product rule, right? So in both cases, what we're really doing is we're trying to identify some product rule. Okay? And if we can see where the product rule is done, then we can undo it and then come up with some result. Okay? So here's 2a squared x squared u double prime u prime plus 2a squared x u prime squared plus 2a squared x squared. Actually, let's write this separately. Let's write this as 2a to the 4th x squared u times u prime minus 2a squared n squared u times u prime equals to 0. Okay. Maybe I should multiply a. Oh, I shouldn't be multiplying by a squared. Sorry, it says 2. A squared is not involved there. Something's a bit strange. Sorry about that. You just multiply 2u prime. Okay. Yeah, of course. All right, so now what I see is that, you know, if I have x squared u prime squared, and let's try to apply the product rule to this one. So we are applying fg prime equals to fg prime plus f prime g. So in this format, what do I get if I do that? I get
X squared.
Oh, this time it's actually the other way. Oh no, it's this one. Okay, so it's oh, what is u prime squared prime? 2 comes down, right? U prime.
U prime, U double prime.
And then you take this inside function and you differentiate it yet again by x, so u double prime, right? So using that, we know that when this is differentiated, this would be 2x squared u prime u double prime, which is exactly this part, right? But then, if you differentiate x squared instead, what do you get? 2x u prime squared, which is this one, right? So this much is same thing as the derivative of this. Okay? Yes?
I think we immediately do it in the first line. The first two term itself is a product rule by x squared u prime. Right?
Yeah. It's you can just see
I mean the
that.
first line, two term of the first line is a product rule.
This one?
Yeah.
Yeah, that's also true. I just this one? No, it's not. Is it?
Yeah.
No. The factor of 2 messes it up. You don't get the factor of 2.
Okay.
Yeah.
Yeah.
So that's why you need to multiply by u prime. Yeah, okay. And by the way, this one also, u squared prime would be 2u, u prime, right? So 2u prime, this much is really d dx of u squared. Okay? All right. But that leaves us with this one, which we don't like. The thing is, we really want x times u squared at some place, right? We know why, right? Because we have x times u times u. If k and m are the same, then it's x u u. So we want that. But we kind of see that this with this, for similar reasons, this is also a product rule if we add something artificially. Right? So let's see. So we want to say something differentiated should give you 2a squared x squared u prime plus 2a squared something here. What goes in there? Can you figure it out? Oh, that's like a puzzle. Yeah.
2a squared x squared u squared.
Close, but not correct.
Not the not 2. I think it's just a squared x squared u squared.
No. Anyone else? See, what really is happening is that this much is the derivative of u squared prime, right? So in the other stage, this one should be in there, without the derivative, right? But the other function that was multiplied should be differentiated instead, right? So what goes in there?
2x u squared.
2ax.
Yeah, 2a squared x u squared, right?
Yeah.
Right? So, you know, a squared can be just pulled out outside. And then this really is the product rule for, what is it?
A squared u squared.
A squared x squared u squared, right?
Yeah.
Okay. All right, so after this hard work, here's what we found. Okay. This now becomes d dx of x squared u prime squared plus d dx, this one here will be the d dx of this but it's not true unless we borrow this. But anything that you borrow, you have to pay it back, right? So you're going to put it back with a minus sign. 2x, 2a squared, xu squared. Right? Is that okay? And then equal to, we're going to move this to the other side. No, we're not. Sorry. Minus n squared d dx of u squared equal to 0. All right, so we did that. So it's hard work. Okay, and now it's the same idea. What do? We put the derivative on, the one that looks like a derivative on the left side, the derivative of x squared u prime squared plus a squared x squared u squared minus n squared u squared. These stay on the left side, but this one you move to the right side. 2a squared x u squared. Right. And then, once you have it like that, what do? Integrate both sides from 0 to 1. Right? Which is going to cancel the d dx, and now you have to evaluate that, right? So you have, I'm missing something. Something's not right. Let me see. Yes. Okay. So, there's a slight problem here. When I was taking the notes, I wasn't paying close attention. Now I noticed something. Okay, so that's going to be the left side, whereas I can pull out the 2a squared outside. And actually, this is what we want, right? It's xuu. So this is the value we want. Let's see what we have on the left side. If I plug in 1, what's u of 1?
0.
0. So it's 1, so you get u prime of 1 squared. Okay, that's what we get. Now when you plug in 0, anything that has x's in there is going to go away, right? Now there's, this one is still 0, but the reason is a bit complicated, okay? So first of all, when n is non-zero, then we saw the graph of the Bessel functions, right? What's the value of the Bessel function at 0?
0.
It's 0, right? The only exception is J0. J0 is a non-zero value, right? But in that case, n is 0, right? In that case, J0 will satisfy the one with n equals to 0, right? So it's still 0, but for a little bit of, it actually has to be dealt in two different cases. When n is non-zero, this u0 will be 0. When n is 0, then we don't care about what this is, so that's gone, right? So either way, we get this equals to 2a squared, and what is to be determined? All right, this took longer than I expected, but we're almost there. So just pay attention just a little bit more. We're almost there, okay? All right. So now the thing is, u of x is defined as jn ax, right? So if I differentiate both sides, I get jn prime of ax times what? Times I see you guys are really tired by now. Come on, I'm just asking you a very simple question. What is if you differentiate jn ax, a is a constant. This is going to be jn prime ax times a, right? Just because of the chain root, right? Okay, therefore u prime of 1, which is like you differentiate first and you plug in 1. So u prime of 1 means you differentiate first and then you plug in 1. It's not you plug in first and differentiate. Okay? So you differentiate and plug in 1 is like plugging in 1 in here, which is a times jn a prime. Right? So this thing on the left side is really equals to a squared jn prime of a squared equal to 2a squared, integral from 0 to 1, x u squared dx, the one that we want. Okay. So we have to solve for this, which gives you integral from 0 to 1 of x u squared dx equals to 1/2 of jn prime of a squared. But what was a? A was j and k, right? And then we also learned a moment ago that if you evaluate j and prime, j and k, there was an identity that we had, right? So what was that identity? It was jn x prime minus n over x jn x equals to jn plus 1 x with the minus, right? So this was one of the identities, and I said when you plug in the zeros in here, this one, by definition of what j and k is, that's gone. So you have this equal to this, right? So that's going to equal to 1/2. Squaring a negative becomes positive, so this is going to be j n plus 1 j n k squared. Okay, so that's what we get. All right, so that's the orthogonality relation. All right, so that's the proof. Okay, but we're still not done yet because now we have to come up with the formula for ak, right? So now let's try to find the formula for ak. How do you use the, so now this ak has nothing to do with this a. Ak is the coefficients of the Fourier Bessel series, right? So how do you get ak? Well, think about this. Let's call this am. So if I take f of x and multiply this by x times j n of j of nm dx, if you integrate from 0 to 1, that's going to be On the right side, it'll be summation x times, well, ak x times jn, jnkx, jn, we multiply j and m, right? So j and m x dx, and we integrate, okay? 0 to 1. Okay, so in most cases, what is this?
0.
Is 0, right? Yeah. Because here, what's the only case it's not 0? When k is n, right? So what you get is on the left side you get 0, 1, x, fx, jn, jnm, dx, and when k and m are the same, you get this value, right? Yeah. So you have to divide by the way, because instead of k we used m, I have to rewrite that. 1/2 j n plus 1. Oh, sorry, this should be just n plus 1, not k plus 1. N plus 1 j n k squared. That should, that's j n m squared, and that's equal to a n. So that's our result today. So the final conclusion is, if you have a function defined from the interval 0 to 1, and you want to know the coefficient ak, let's write down for ak, because that way we can use this. It's from 0 to 1, x, fx, jn, jnk dx, divided by 1/2 jn plus 1 jnk x. Right, there should be x there. Oh, keep forgetting the x's, sorry. Right. Oh no, this one doesn't have an x. That one should have an x. Or else it's you can't do it in the interval, right? So this one is squared. Okay. So this is the formula for the Fourier series. Fourier Bessel series.